Hello everyone, how's it going? My name is Dan the Tutor. In today's video, we're going to be looking at problems where I give you a piecewise function, which, if you forget, piecewise functions are functions that look like this. They have the curly bracket, and they have one portion for the top part of the graph and another portion for the bottom part of the graph. And we're going to be checking if these functions are continuous at the point, in this case it would probably be 2. This is almost always seen on the first exam of Calc 1 because it is such a popular topic. So I'm going to tell you how to solve these problems, and I'm also going to tell you a shortcut you can use if your professor allows you to use shortcuts. So technically this is a 3-step process if you want to prove this is continuous. The first step involves proving that f of a exists, where a is the point we're looking at where it's continuous. In the example above, it would be 2. And to prove that it exists, you literally just say, hey, I have greater than or equal to. The equal sign means that we're fine, especially because you can plug in 2 here for x. 2 plus 1 is 3. I don't care what the value is, I just care that it exists. There's other problems where either the denominator is 0 or you're missing an equal sign altogether where that first check is going to fail. But 99% of the time, the first check passes. Most of the time, we fail because the second check fails, which is where we say the limit as x approaches a, f of x, exists. And to prove that, you need to check the limit from both sides. In other words, limit as x approaches a from the left needs to equal the limit as x approaches a from the right. If it doesn't, it does not exist, and therefore f of x is not continuous. And basically here, the first equation is greater than, so that would be a from the right, and the second equation is less than x less than 2. That would be when we plug into a coming from the left. And if these two things equal each other, then we pass the second check, and then finally the third check usually just works out. The third check says the value at a needs to equal the limit as x approaches a. And that third check should always pass unless you have some situation like this going on where the function has a hole in it and the hole is filled somewhere else on the graph. This is where the third check would fail. Now obviously we're not talking about graph problems right now, we're talking about equations, but there are times where this third check will fail, and it's usually when I have 3 functions in my piecewise function. And obviously I can't add it here because I already have all my ranges covered, but usually it's when I have 3 functions in my piecewise function. That's usually when that third check fails. So let's go ahead and look at some examples now. For the first one, I want to know if f of x equals 2x minus 3 for when x is greater than or equal to 1, and 1/2 x minus 3/2 for when x is less than 1. I want to know, is this continuous at x equals 1? And I want to use that 3-step method. So the first thing I'm checking is I want to know, does f of a exist? In this case, it's 1. I'll tell you it does exist, and I know that because when I look at the top equation, that has the equal sign. So if I plug in 1 in for x, 2 times 1 minus 3, that's negative 1. And again, I don't care what the value is, I just care that it exists. So in other words, we passed the first check. Now for the second check, I need to find a 2-sided limit. First I'll do limit as x approaches a from the left. From the left, that's going to be the bottom one because it's less than. X is less than 1. So if I plug in 1 for x, which is what I want to do to solve this limit, just plug in 1 for the x in the bottom equation, it's going to be 1/2 times 1 minus 3/2. That is going to equal 1/2 minus 3/2, which is just negative 2/2 or negative 1. And then of course, I want to check the limit as x approaches 1 from the right. And I just realized here, I wrote a, I should have wrote 1 there. So I'll fix that now. That looks better. And since it's 1 from the right, it just ends up being the top equation, which if you think about, I already plugged in 1 for that one already, and I got negative 1. So I'm just going to put negative 1 there. And so as you can see, since the limit from the left equaled the limit from the right, that means the 2-sided limit is going to exist, and it's going to equal negative 1. And then the third and final check, I need to know if f of 1 is equal to the limit as x approaches 1. And here I get negative 1 equals negative 1. Check. So there, I passed all 3 checks. We would say yes, it is continuous. And there we go. That's all we have to do. Now, like I mentioned earlier, there is a shortcut. The shortcut is you literally just plug in 1 into every branch. If there's 2 branches, plug it into both. If it's 3 branches, plug it into all 3. And you'll get -1 for both, so immediately we know it's continuous that way. The reason why I don't do this every time is because if it's, for instance, a free response question on the AP exam, they will not give you full credit for that. You need to give the correct notation, which is to say you're checking the value, then you check the limit, then you set the value equal to the limit. They're looking for all 3 of those points. So in other words, if you're taking the AP exam in the spring, I want you to do it this way. Or if your teacher or professor asks you to use this 3-step process. But for the next 2 problems we're doing today, I am going to be doing the formal 3-step method. Here is the second one. F of x equals, and this piecewise function is going to be 3 parts. The first part is 5x, and that's when x is less than -2. The middle branch is just going to be 1, and that's when x equals 2. And then the final branch will be 3x minus 4, and that's when x is greater than -2. So why don't you pause the video, try this on your own. You can use either the shortcut or the formal method, whichever you prefer. And when you're ready to see the solution, unpause the video. Okay, so the first thing I'm doing, using the formal method, I want to plug in the value at -2. And so I'm looking for the equal sign. The equal sign is the middle branch. And a lot of people here will write the answer is -2, but they would be wrong. The answer is just 1. If there is no x to plug into, then you literally just use the number they give you, which in this case is 1. And since 1 exists by definition, as opposed to not existing or being a 0 in the denominator, which cannot happen here, it looks like we pass the first check. Now for the second check, 2-sided limit. First, I'll do limit as x approaches -2 from the left. If I'm talking about the left, I'm talking about less than sign. That is going to be the 5x one. So that's going to be 5 times -2, which is -10 for the left. And then for the right side, that's going to be the 3x minus 4. So I have to plug in -2 for that. That's going to be -6 minus 4, which again is -10. And once again, these two are equal to each other, which means the 2-sided limit exists, and it's going to equal -10. We pass the second check. If we failed the second check, or even the first check, the problem would be done. We would say not continuous and move on as soon as any of the 3 checks fail. But since we passed the first 2, I do move on to the third, which is to check that f of -2 equals the limit as x approaches -2. And as you can probably tell, this is not going to be equal. And so you would just say not continuous for that reason, and we're done. Okay, now we just have one more I want to look at today. For this question, it's going to be a little bit different. I want you to solve for a value of k so that f of x is continuous. And let me give you the function f of x, which is going to be a piecewise function with 2 parts. The first part is x squared minus 4 over x minus 2, and that's when x does not equal +2. And then for the second part of the piecewise function, it's going to be x minus k, and that's when x does equal 2. Now there's 3 things that are different for this problem than the last problem. First thing that's different, we have a k obviously, and we need to solve for it. Second thing that's different, we have the not equal to sign here, as opposed to greater than or less than. And the third thing that's different is we actually have a potential domain issue with this guy, specifically at x equals 2. Luckily, x will never be 2. It specifically says x does not equal 2. And the reason why that's significant is because, as you'll soon see, x squared minus 4 over x minus 2 will cancel a little bit, which is the factor and cancel method of solving limits. So how do we solve this problem? Well, basically, we need to realize that in order for this thing to be continuous, x minus k needs to equal x squared minus 4 over x minus 2 at the point x equals 2. Furthermore, the x squared minus 4 over x minus 2 can factor to x plus 2 times x minus 2 over x minus 2. The x minus 2's cancel, and this is looking really good already, because now we have x minus k equals x plus 2. Obviously, it looks like I'm not using the formal method to solve this one, but it really doesn't matter. The only thing I want to mention for the formal method, if I wanted to take the limit as x approaches 2 in this case, I would not do the left and the right limit, because one thing you should know about the not equal to sign, the not equal to sign covers the greater than and the less than sign. In other words, it covers the left and the right limit. So I don't need to check left and right limit, I just have to check x squared minus 4 over x minus 2. Again, we get a factor and cancel, so all of that's already taken care of with this step. And again, we have x plus 2. So now I'm plugging in 2 for x. 2 minus k equals 2 plus 2. So in other words, 2 minus k equals 4. Subtract 2, negative k equals positive 2, which means the correct value of k has to be negative 2. And there we go. That's how we solve problems like that. So hopefully that answers all of your questions today. If not, please post them in the comments. Thank you all for watching. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.